In this video, I'm going to be teaching you what is instantaneous rate of change and how to derive the first principles formula for calculus. Now, I have a question for you. If I asked you what is the gradient of this function here that I have drawn, the gradient of this quadratic, what would your answer be? You would probably think that's a stupid question, right? In every single capacity that you've done gradients before today, you have learned that gradients only apply for straight lines. Okay, so you have learned that if I have a line like as such, this blue line here, you can work out the gradient of this line by simply picking 2 points that lie on my line and working out both the rise as well as the run. If I work out the rise and the run, I can just do my gradient is the same as the rise over my run. And that's what a gradient has always been applied to in every context we have done before. But let's just forget about our line example. Let's just look at our function that's over here, the quadratic. That would be a stupid question to just ask, what is the gradient of the entire curve? Because you can see, towards the left-hand side of my parabola, my graph is decreasing, so the gradient will be negative. For every one step in x I make, there is a negative step in y, which means I have a negative gradient. But as you pass the turning point, right? In fact, if you just look at the turning point, for every one step in x you take, there are no increases in y at this point. And for every point you take here, if I take one step in x, there is a positive step in y, which means there is a positive gradient. But what does it mean at a single point? I want to know how much is this point just here. Is it rising, or is it falling, or is it just stationary? Well, I'll make it a little bit easier for you. If I draw a line that is tangent at this point, a line that's tangent to this point, you can clearly see that that tangent line is rising. Okay, and you can see that the point that's over here is increasing in the direction of the tangent line. So easy. All we have to do to work out the gradient of this point is just to work out the gradient of this line. Okay, easy. Let's just do rise over run. But hold on a minute. I literally don't have any other point that lies on this line except for this one. And even worse, this is just some arbitrary line. So there's no way for me to work out another point. So what do we do here? There is a solution for this problem. The first thing we can do is let's just pick another point on this parabola that isn't the light blue one. Let's say this purple line here. And I'm going to give this light blue dot, I'm going to give it coordinates of x, comma, f of x. So the x value is just some arbitrary x value, and the y value is some value, which is f of x. And I can also extend that to my graph and say the equation of the graph is y equals f of x, more specifically the parabola. So now that I have this, let's label the second point in purple. Let's say the coordinates of my purple point, I'm just going to draw it away from the actual graph. I'm going to say it's still some arbitrary x value, right? But it's just taken like a nudge this way. It's taken a little nudge in towards the right direction. So we started off at this x value, but we've taken some value, let's say h. Okay, we've gone some h units to the right. So we can say the x value is simply x plus h. Okay, and let's suppose the y value is simply the y value of the parabola, which in this case will be f of x plus h. Okay. To work out the gradient of this orange line, which is our eventual goal, our entire goal of this exercise here is to work out what is the gradient of the orange line. Let's start off by taking the gradient of this line here, the line which connects these 2 points together. Okay, we need to work out the gradient of the purple line that we have. Well, that's pretty easy now because we have the coordinates of 2 points and we can easily work out the rise over the run. And I'm going to work out the rise over the run in red. So what is the rise? What is the change in the y values between the two coordinates? Well, I finish off at f of x plus h. The y coordinate of this point is f of x plus h. And the y value of this point here is simply the same as the y value of the blue point, which is just f of x. So we want to work out what is the change in height, the change in the y's of these 2 points. It's simply just f of x plus h minus f of x. Now, what is the run? Remember, the formula for gradient is rise over the run. So what is the run, the change in the x values? Well, the final x value of my purple point is x plus h, and the initial x value over here, the light blue point, is just x. So it's x plus h minus x, and that just simplifies down to x. Sorry, it just simplifies down to h. Okay, so now that we have this, we can work out the gradient of the purple line. Wow, very easy and cool for us, except that wasn't the question I asked. The question I asked was, how do you work out the gradient of this orange line? Well, I have an idea of how we can make it a little bit more accurate. And one way I could make it more accurate is, why not just move this purple point closer to the light blue point? So what I'm trying to say is, instead of having it so far away over here, the purple point, instead of keeping it all the way over here, why not bring it closer to like here, for example? Okay, why don't we just bring it closer to here? And I'll demonstrate what that looks like. We have that point there, and let's draw a line that connects both the light blue as well as the purple points. Now you can already see, just by this graph here, the gradient of this purple line looks much more closer to the orange line than it previously did. Now obviously it's still not the exact same, it's still a little bit different, but we've made a little bit of progress. So we can still say the coordinates of this point is x plus h, comma f of x plus h. And in order to work out the gradient of this purple line, it's still the same formula, that hasn't changed. Okay, it's still the same f of x plus h minus f of x all over h. So why don't we keep taking this thing that I just did and repeat it several times? We move this purple point closer and closer and closer and closer towards this light blue point until eventually it's so infinitesimally close to the light blue line that you can pretty much say it is the light blue line. And what I'm trying to say is, the value of h, each time we keep making this purple point closer, will start decreasing. The value of h will start decreasing. So let's say the little nudge that we had before, let's say that was a value of 2. So we did a little nudge in x by 2 units. Then we can do it by 1 unit. Then we can do it by half a unit. Then we can maybe even do 0.001 units. So that would be even more accurate because h is very low. But let's just keep going so that the little nudge in h is 0.0000000 forever and ever and ever, 0001. Okay, let's make sure that this goes forever and ever and ever and ever and ever, such that it pretty much approaches 0. Okay, it's pretty much the same thing as 0. That's our entire goal here. And the operation of doing that is simply by using a limit. We're going to say we can't actually equal to 0. H cannot equal to 0. Why? Because there's 2 reasons. One, the entire exercise of h was to create 2 distinct points. So if we don't have 2 distinct points and h was just 0, we would be back to our original problem, which is we have only 1 point. How on earth are you going to work out the gradient of the line with only 1 point? So we can't have h equal to 0 for that reason. The second reason is, if we look at our gradient function, h, if it was 0, you'd be dividing by 0, and that's a big math no-no. So we're not allowed to do that. So instead of actually letting it equal to 0, the calculus way of saying that is the limit as h approaches 0. And we put a box around it, and this is our differentiation by first principles formula. We're saying let h not be 0. Okay, we're not saying it's actually going to equal to 0. We're going to say, just let it get so close to 0, like infinitesimally close to 0, which is opposite of infinite. Infinite is referring to large numbers, whereas infinitesimal is referring to very, very small numbers. So let it get infinitesimally closer to 0 so that it pretty much is 0. And that would exactly give you the gradient of this orange line. And that is how you do differentiation by first principles. That's where this formula comes from, in order to work out the instantaneous rate of change at a single point.